Now, going through a polarizer is only one way to cause polarization in light. There is another prominent way to polarize an otherwise unpolarized beam of light, and that's by reflection. Very simple, reflection. Let me show you how that works. Okay. What I have here, first of all, is some background knowledge. I have an electron or any charged particle, and I let it oscillate. Okay, it oscillates in this direction. When it oscillates at a certain frequency, it's going to give off radiation of the same frequency. Okay, we call it the dipole radiation. Okay, we call it dipole radiation. And the thing about the dipole radiation is that if it oscillates in this direction, okay, say in this direction, it can only give off radiation in a direction that's perpendicular to it or at a side angle. There is no radiation emerging from the same direction of oscillation. That is because light, or any electromagnetic wave for that matter, is a transverse wave. So if you oscillate in this direction, you cannot propagate in the same direction. Okay? So again, when this electron oscillates in this direction, the most prominent oscillation electromagnetic will emerge from a direction perpendicular to it, like this. And some of it will go this way, some of it will go this way, but nothing will go that way. Okay? Nothing will go along the direction of oscillation. That is some basic knowledge we have. Now, with that in mind, let's look at how reflection can cause polarization. Suppose I have a reflection from the border of two media, N1 and N2. Now, let's say the incoming wave is unpolarized, which means it's got a 50-50 split between oscillations within the plane, within this plane of the paper, and perpendicular to the plane. Okay, so this dot here represents oscillation perpendicular to the plane. This red vector represents oscillation within the plane. Okay, within the plane. Now it comes at an angle, and then what happens when this radiation hits the border between two media? Well, the reason why light can reflect and transmit is because the electromagnetic wave carried by the incoming wave will cause the electrons on the surface of this medium to oscillate. Okay, to oscillate. And as they oscillate, they will give off secondary radiation in this direction and that direction. Okay, and it turns out that the reflected wave is partially polarized, and sometimes under right circumstances it can be 100% polarized. How does that work? Well, it turns out that at a certain angle of incidence, the reflected wave will have only one oscillation direction left, and that is perpendicular to the plane of the paper, like this. They can only oscillate in this direction. The red vector has been totally removed, so it's a linearly polarized wave. Why is that? Well, this happens when the reflected wave and the transmitted or refracted wave are 90 degrees away from one another. This is 90 degrees. Okay, that usually doesn't happen, but when that happens, you know what that means. The reason why waves can oscillate, the transmitted wave is like this, okay, in that direction, is because the electrons on the surface will oscillate in such a way that is perpendicular to the propagation direction. Okay, see, electrons oscillate in this direction, give off wave in that direction, perpendicular, like this. Okay, so that means the electrons must oscillate the electrons must always oscillate in such a way that is perpendicular to the transmission direction. But the same electrons are also responsible for causing a reflected wave. But wait a minute, the electrons oscillate perpendicular to this direction, and at this angle, I said at this angle, this is a special angle, these two have to be 90 degrees from another. That means the electrons must oscillate in a direction that's parallel to this direction, right? Parallel to the reflected direction. So electrons oscillating in this direction can never give off any wave in this direction. So that's why the red vector is totally removed from the reflection. Only the black vector still persists. The black vector, the electron can oscillate perpendicular to paper, and they of course can transmit that way. Okay, so this is a special angle. It's an angle such that the reflected wave and the refracted wave are 90 degrees from one another, because of the dipole oscillation of the electrons, there is no component in the electromagnetic field, electric field, that is perpendicular, that is parallel to this plane in the reflected wave. Okay, so it becomes totally polarized. This is a special angle called the Brewster's angle. Okay, Brewster's angle. How does one calculate Brewster's angle? Well, quite simple. We call this angle theta p. Okay, p for polarization. We know that sine theta 2 over sine theta p, that equals n1 over n2, right? Am I right? That's the law of refraction, right? Theta 2 over theta p. Remember, these two angles are the same, okay? But on the other hand, these two angles add up to 90 degrees, so those two also add up to 90 degrees. So therefore, theta 2 plus theta p equals 90 degrees, and therefore, theta 2 is 90 degrees minus theta p, so sine theta 2 really is sine of 90 degrees minus theta p, right? And that is cosine theta p, see that? Cosine theta p. So if cosine theta p over sine theta p equals n1 over n2, and therefore you flip that over, you get sine theta p over that's tangent. Tangent theta p equals what? Equals n2 over n1. Right? This is the formula that gives us the Brewster's angle. Okay? Gives the Brewster's angle. For example, if this is air, this is water. When light gets reflected off water, when it bounces back at this particular angle, when n2 is 1.33, that's about, and n1 is about 1, you can calculate this angle. Okay, you can calculate Brewster's angle. So you get 1.33, and you find a tangent. Okay, let's see what that equals to. It's about 53 degrees. Okay, 53 degrees. So air, water, surface. Theta p is about 53 degrees. So if light comes in at 53 degrees of incidence, after getting reflected off of water, the reflected wave is 100% polarized. Okay, of course, that's just a special case. If it's not 53 degrees, it's not going to be 100% polarized, but this red component will be severely restricted in the reflection. So it's going to be partially polarized. Now, is there any use out of it? Well, one of the things you might have heard or you have used yourself is called polarized sunglasses. Okay, these things are quite useful when you work around a large body of water, such as you go to the beach. Okay, you find that polarized sunglasses work better than unpolarized sunglasses. A polarized pair of sunglasses, light going through, it's basically, it's made of two polarizers. So light going through can only certain direction can go through. And then the nice thing about this is that it can reduce glare from reflection. Okay, imagine sunlight get reflected off of water. You get a lot of glare. It's very bright, the water surface. But remember, these beams are polarized. So if you put a polarizer in front of your eyes, that can block a lot of these reflected beams. Okay, so it will look bright. Everything will look cleaner. You can cut down on glare. Similar things happen when you do window shopping. Okay, you try to look through the glass and see what's behind. Sometimes you get a glare, you get a reflection from the glass. That's undesirable. How do you cut down the glare? Well, remember, the glare is partially polarized, if not 100% polarized. So again, you can put a polarizer if you want to take a photograph of what's behind glass. Okay, what you can do is you can attach a polarizing piece, okay, or polarizer in front of the lens, and that can block a lot of the reflection, because it's polarized, so allow you to see more clearly behind it. Okay, so that is an example of called polarization by reflection. There is yet another important way to polarize, to cause polarization. It's called polarization by scattering. By scattering. What's scattering? Well, an example of scattering: light from the sun interacts with air molecules. Okay, it causes the air molecules to oscillate, and as a result, the air molecules themselves become the source of secondary radiation, so they will give off light. Okay, that is called scattering. All right, let's look at how light can be polarized by scattering. This, in fact, has to do with a lot of the things that we see on a daily basis. That is, why is the sky blue? Why is the sun yellow in the middle of the day, and yet during the sunrise and sunset, the same sun appears to be red? Why is that? All these things really have to do with the same issue of polarization by scattering. Okay, now first of all, light from the sun is not polarized. Okay, suppose light from the sun comes this way. So this is the light ray from the sun coming this way. There is no polarization, which means the electric field is oriented everywhere within the plane that is perpendicular to the direction of propagation, which we call x-axis. So it can oscillate freely in a y-z direction. Okay, but on the other hand, if you look away from the sun, okay, now without any air molecules, if there's vacuum, okay, if you look away from the sun, you look this direction, you don't look that direction, you're not going to see the sun at all. Okay, you don't see any brightness. It's just totally dark. As a matter of fact, that is true. The reason why we can see bright sky in the daytime, even if we don't look directly into the sun, is because there are air molecules that help scatter the light from the sun. If you are out of the atmosphere, you're in space, you look into a star, it's very bright. You look away from it, it's totally dark. Okay, right? Either totally bright or totally dark. You don't see any blue skies or anything like that. That is really the work of the atmosphere. So if you look, say 90 degrees away from the light of the sun, sun comes in this way, you look that way, what do you see? Well, there are two possible oscillation directions. One is the z direction, the other is the y direction, right? And it's actually a combination of the two that can give you any oscillation direction. But in order for that beam to reach your eye, it has to travel this way. When it travels this way, it cannot possibly oscillate in this direction anymore, because otherwise light would be a longitudinal wave, right? It oscillates and travels in the same direction. So this beam is devoid of any oscillation in the z direction. There is only oscillation in the y direction. That's why after it travels in this direction, you only see this component. And that, of course, is polarized. It means it can only oscillate in the y direction. So when you look sideways from the sunlight, so sun comes in, we look at sideways, you find the sky, the light from the sky is partially polarized. Okay, it's partially polarized, and you can actually verify that if you take a polarizer or you have a polarizing pair of sunglasses. You take that outdoors and you look at a direction away from the sun directly. Okay, away from the sun directly, and you rotate that polarizer, you find that you see a variation of the intensity of the brightness coming through, which means the sky is partially polarized. Okay, it's partially polarized. Except when you look directly at the sun, then of course there is no polarization. Okay, now how does that have to do with the color of the sky and the color of the sun? Well, it turns out the scattering effect is different for different wavelengths. The same physicist, Lord Rayleigh, who gave us the Rayleigh criterion, okay, also did a calculation of the intensity of the light coming from scattering. It turns out that scattering is more prominent for longer wavelengths, actually for shorter wavelengths. Okay, the intensity of the scattering goes like 1 over lambda to the power 4. Okay, now we're not going to do the calculation here, but it can be proven. It's something like that. That means for different wavelengths or different colors from the sun, those with shorter wavelengths get scattered more greatly. Scattering brings the light in sideways. Okay, if there's no scattering, light can only go directly through. You cannot see anything from the side. So when you look at it from the side, okay, look at the light from the side, you find that you get more light with shorter wavelengths, less light with longer wavelengths, because longer wavelength has less scattering, which means light can go through more directly. Okay, now light from the sun has all kinds of colors, right? Red, green, yellow, blue, and so forth. But those with longer wavelengths can go through more easily. Those with shorter wavelengths get scattered more frequently. That is why what you see when you look at the sky away from the sun, you see a color distribution towards the shorter wavelengths. Okay, because the shorter wavelengths gets greater amount of scattering. Now, purple has the shortest wavelengths within visible light. But the problem with the sun is that it doesn't produce a lot of purple light. Okay, what's the next shortest wavelengths? It's blue. All right, that is why the sky looks blue when you look at it from the side. Look directly. You look away from the sun in the middle of the day. You see the sky is blue. That is because of the scattering. Okay, that's because of scattering. Now, why is the sun yellow when you look directly into it? Well, when you look directly into it, you don't worry about the scattering effect. Okay, you don't worry. I mean, there is some scattering, but not that much. Okay, not that much. In broad daylight, there is not that much. In fact, here is the Earth, and the sun is. We're talking about the middle of the day. Okay, we're talking middle of the day. So the sun is here. It produces all kinds of frequencies. And here is the atmosphere. Let me draw the atmosphere. The sun has to go through this much atmosphere before it reaches your eyes. It is not all that thick, so you get some scattering going on to the side, so it looks blue from the side. But still, the most prominent radiation from the sun is yellow. Yellow has more intensity than any other color. That's why you look directly, the sun still looks yellow to you. Okay, even though you look sideways, because of the enhancement of scattering for shorter wavelengths, it looks blue. On the other hand, why does the sun appear to be red during sunrise and sunset? Well, during sunrise and sunset, where is the sun in the sky? It's not directly overhead anymore, right? It's somewhere there, right? Near the horizon, right? So now, this time, light from the sun will have to travel a much longer distance through the atmosphere. You see how much longer this is compared with that? Okay, and along the way, it has to be scattered. And so more scattering will happen for shorter wavelengths, so scattered sideways, leaving only the longest wavelengths to be prominent. The longest wavelength, of course, is red. Okay, so it is because of the prolonged path the sun has to travel through the sky during sunrise and sunset that enhances the scattering effect. So more of the shorter wavelengths get scattered. Even the yellow gets scattered a lot. The red, on the other hand, has longest wavelengths, so it gets scattered less, the least. Therefore, it appears to be yellow. It appears to be red. Okay, because there is not much scattering going on. You can still see it. So you see, the same basic physics explains all these things. Why is the sky blue? Why is the sun yellow during the day and red during sunrise and sunset? It's all part of polarization by scattering. Okay, I must point out that there are yet other mechanisms that can cause polarization. One of them is called polarization by double refractive crystals. We use that a lot, but we don't have time to discuss that. There are other mechanisms. Okay, so we had a brief overview of optics. I must tell you that the amount of optics we study is far less from what's adequate for a lot of you in the future because of time constraint. A lot of you will be studying a lot more about optics, especially how you combine optics with electronics. These days, this is a very important field in engineering. But hopefully we give you a basic overview of optics so that you can continue your future study in this field if necessary. And with that, there goes our Physics 1C. Hope you had a good time, and remember, these are just the very basic things. Most of you will have to study a lot more about electricity, magnetism, and optics in the future. Thank you very much. I hope you had a good time. Okay, I certainly did. Thank you.